Hi everyone, my name is Yuanhui Wu. I'm a PhD student in Speech Processing and Machine Learning Lab, National Taiwan University. Today, I'm going to present our work, One-Shot Learning for Speech Separation. This is the overview of our presentation. I'll first introduce our scenario, proposed methods, then my partner Guanbo Huang will introduce the experiment setup and results, and end with the conclusion. First, I'm going to talk about scenario. Speech separation aims at separating the voice of each speaker when multiple speakers talk simultaneously. Our paper mainly focuses on the blind speech separation task. Blind speech separation refers to a problem where both the sources and the mixing methodology are unknown. Only mixture signals are available for further separation process. A key aspect related to training data is that it needs to be representative of production data that occurs in real-world applications where the machine learning solution is deployed. If the production data is completely different, the results are likely to be useless. In the speech separation task, the separation model often encounters different sets of speakers in the real-world scenario. Also, there is some background noise which does not appear in the training data, thus causes a data mismatch problem. A feasible approach is to improve the generalizability of the speech separation system, is to establish a gigantic model which is trained from mixtures covering different speakers and acoustic environments. It is quite challenging in two aspects. First, it is hard to cover all speakers and acoustic environments. Second, training the machine learning model requires a great amount of data. However, it is impractical to ask the users to record lots of speech data. In our approach, few data is needed. We just need to collect one speech utterance from each new speakers to adapt our separation model to new conditions. These data can be collected by speech enrollment process, shows the feasibility in real-world scenario. So how can we learn a good separation model by using only one utterance? We use meta-learning to solve this problem. Second, I'm going to talk about our proposed methods. Our goal is to solve a new task by giving only one utterance. So what is a task? A task is defined by the dataset and the loss function. The loss function L is SISNR score, which is shared across tasks. The difference between tasks is the distribution over the data. In our work, we generate mixtures from different sets of speakers. Thus, data with mixtures generated by the same speaker set forms a speech separation task. Here is an example. The data generated by the green and the purple speaker forms a task. First, we selected 3 utterances of each speaker from the source dataset. Then, we picked one utterance from each speaker to create a mixture in the training set, and the rest of the mixtures form the testing set. The training set is also called the support set, which is annotated as tau support indexed with J, refers as the support set of the task J. And the testing set is also called query set, which is annotated as tau query indexed with J. After seeing the data in the support set, the model should perform well in the query set. So here we have one mixture's utterance in the support set from the meta-testing task. Because there is only one example here, we call it one-shot learning. The goal is given this one example, separate the other mixtures come from the same set of speakers. In the meta-learning dataset, there is a meta-training set and a meta-testing set. A meta-training set is a combination of all training tasks, and the meta-testing set consists of the testing task. In meta-learning, the goal is to able to leverage the meta-training data from other tasks in order to solve this meta-testing task and learn the one-shot separation. So the way to do that is to structure the meta-training task data into support set and query set, which is the same as what we are doing to the testing task. And we perform meta-training across these training tasks such as after it sees the mixture and the sources from the support set, it can successfully separate the mixtures in the query set. By doing this, we hope to separate the mixtures from the held-out speakers, especially from the one-shot learning. So what is the meta-learning problem? In this figure, we want to perform separation on the data in a query set of the task J. The parameters of the neural network are corresponding to the function, which is annotated as lowercase f. This parameter is specific to each task, so theta j is specific to the task j. Now, we want to leverage the information from the support set of the task. We feed the data in the support set to the learning algorithm, which is annotated as uppercase F. This learning algorithm is shared across tasks that tries to generate the task-specific function, lowercase f, for each task. And that is why we call meta-learning learning to learn, because we're trying to learn the learning algorithm, uppercase F. You might wonder, what is learnable in a learning algorithm? It could be the network architecture, or the initial parameter of the neural network, or the optimizers used during training, and so on. In our work, we focus on the initial parameter of the neural network. So the complete problem can be referred as generating a set of task-specific parameters, can be a function that takes the data from the support set and output the task-specific parameters, theta I. By feeding the data in the query set to the task-specific model, we can calculate a SI-SNR loss between the estimated sources and the target sources. So we want to learn the parameter theta, such that the task-specific parameters theta I generated from it is good for the query set. So how good is the initial parameter theta? We define a loss function, L meta, to define the goodness of the initial parameter theta. The meta-adjective function can be viewed as minimizing the meta-loss function, which is defined as the summation over the SI-SNR loss corresponding to the query set and the task-specific parameters across all tasks. So the whole process would be, we want to optimize the initial parameter theta. We first sample a batch of tasks. Then we sample disjoint datasets from each task, which is the support set and the query set. Furthermore, we want to compute the task-specific parameters theta I from the initial parameter theta. We perform a gradient descent on the SI-SNR loss calculated over the support set. At last, we updated the initial parameter theta with respect to the meta-loss function, which is corresponding to the task-specific parameter theta I and the query set. Then, we'll repeat these 4 steps iteratively using the gradient descent optimizer. ANIL, short for almost no inner loop, is a simplified version of MAML. ANIL is feature with feature reused. It believes that the meta-initialization already contains useful information that can be reused. Assume the model theta can be split into 2 parts: generalized feature extraction layers, which contains useful information that can be reused, and the task-specific layers omega, which should be different from tasks. Thus, only task-specific layers should be updated while performing task-specific adaptation. Here is the figure of the speech separation model. It contains an encoder, a separator, and a decoder. We can pick the separator module as our task-specific layers, or we can pick the encoder and the decoder module as the task-specific layer. We will later show that the separator is a better pick for the task-specific layers. This is the formulation of a ANIL algorithm. We can say that it is quite the same as MAML. The only different part is that the algorithm replaces all the model parameters corresponding to different tasks, theta I, to the task-specific layers, omega I. Only the task-specific layers are updated for task-specific adaptation.
Hi, I'm Kwanpo Huang, graduate student from the Speech Processing and Machine Learning Lab in National Taiwan University. I will present the rest of the contents of our paper. In other experiments, we use convolutional testnet with the configuration that yields the best performance as our model. Since our method is model agnostic, we can switch to different models. We use WSJ02 mixed meta as our training task, and W2 mixed meta, VCTK2 mixed meta as our testing task. In the training task, There are 4,050 tasks for training and 1,000 tasks for validation. The testing tasks are similar to the training tasks, but with additional mucin noise. The experiments include 3 phases. The first phase is pre-training with the mixtures in the training tasks. We pre-trained our model on the WSJ02 mixed meta training set for 100 epochs. The best model was the 84th epoch, which had the best validation loss during pre-training. We refer to as best in the further slides. Apart from the best model, we also chose the model trained for 50 epochs, which we refer to as half in the further slides. The second phase is performing meta-learning with the training tasks. Models further trained with meta-learning use these 2 model checkpoints as their pre-trained models. The final phase is fine-tuning the whole model parameters on the testing tasks. During the fine-tuning phase, we fine-tune the different parts of the model. The first option is to fine-tune the whole model. We denote this as M. The second option is to only fine-tune the separator. We denote this as AS. The third option is to only fine-tune the encoder and decoder. We denote this as AC. Now, I will be talking about the results of our paper. Will the performance improve by applying meta-learning after pre-training? To figure this out, we compared the performance after meta-learning with the baselines that were only pre-trained. From the results, we found out that training with mammal from the best pre-trained model yields the best performance on Libri2 mixed meta. We also found out that training with mammal from the half pre-trained model yields the best performance on Libri2 mixed meta with noise. Training with mammal without pre-training yields the best performance on VCTK with and without noise. From the previous experiments, we can conclude that all the best results are from the models trained based on the mammal method. Meta-learning methods can help adapt speech separation models not only on utterances of unseen speakers but also on utterances with noise. During the meta-learning phase, we adapted the model on different model parameters. NILS means that we only fine-tune the separator. NILC means that we only fine-tune the encoder and decoder. Adapting the parameters of the separator performs better in all the datasets, showing that the separator is the task-specific module, while the encoder and decoder are the modules that generalize reused features. However, we can see that updating and fine-tuning the whole model is the best way in the meta-learning methods. Thus, we can conclude that rapid learning is the best way for a speech separation model to adapt to new speakers and noisy environments. We also conducted ablation studies. We made some comparisons about whether pre-training is needed and whether fine-tuning different parameters affect their performance. To know whether pre-training affects the performance, we tested the performance of the 2 pre-training models. We can see that when we use the half pre-trained model, the performance drops a little bit. These 4 datasets have a performance drop when we switch from the best pre-trained model to the half pre-trained model. Thus, we found out that performance drops in most cases while using the half pre-trained model. However, we can see a different result when training with mammal. Though we use the half pre-trained model rather than the best pre-trained model, the performances are still better in most of the cases. This suggests that we do not need to pre-train our model using all the training epochs in mammal. We also wondered about the performance of fine-tuning different parameters after pre-training. We found out that fine-tuning the separator module outperforms fine-tuning the whole model in the autoencoders. This suggests that the layers in the separator play a more important role in the task-specific layers in the speech separation model. What about evaluating without fine-tuning? Compared to Model 1, which is not fine-tuned after pre-training, Models 3 and 4, you can see that their performance are better than Model 1. And Model 2 suffers from performance degradation. The results show that fine-tuning on task-specific layers is more effective than pre-training without fine-tuning in most of the cases. Finally, we came up with the following conclusion. We proposed meta-learning approaches on speech separation with the aim to quickly adapt to new situations. Our proposed methods outperform pre-training on new speakers and noisy conditions. The separator plays a more important role for the task-specific module in speech separation. Our presentation ends here. Thank you for listening.